Okay. Hello, everyone. Today we're just gonna go over number six is tree method walkthrough. Instead of doing number five, which we have gone through in section, we're gonna try with different recurrence just for extra bit of practice. So instead of doing this recurrence that we did in section, we'll be focusing on in this video this recurrence right here. And this recurrence is directly from 6C for your own reference. And so why don't we just try go ahead and solve this. And I'm using number five in here because number five actually has really helpful guidelines into a step-by-step guideline on how to properly solve tree method. So I highly recommend using number five as sort of like an outline into how you want to solve problems in tree methods, essentially. All right, so in this problem, we have this recurrence. It seems like in this case, we have a base case, which does amount of, some constant work, one, if n is equal to one. And we have this recurrence, basically like recursive call. So it seems like there's 8 recursive calls given by this 8 right here. And at each recursive call, our input gets smaller by n/2. And at each non-recursive call, non-base case, we do 4 n squared amount of work. Right? And so let's kind of like go to step by step on this. So A asks, what is the size of the input at level of I? Well, let's sort of kind of draw out the tree. Well, in the beginning of a tree, right? We'll start with one node, right? And in this case, our input at our first top of a root of a tree will be basically n, right? Because we start with n things essentially. And the work we do at that the top of our node will be given by 4n squared, right? Given by this right here. Right? And then since there's 8 recursive calls, there should be 8 branches coming out. 1, 2, 3, 4, 5, 6, 7, 8. All right. And within each recursive call, it's going to have its own input and work, and this one's going to have its own input and work, and so forth on. And I'm not going to draw all these out just for sake of time and my hand. And so for here, we know that when we go into our first recursive call, we know that our input gets divided by half, essentially. Right? And so what happens is that our input in this case, in our second level, will be n/2. And work in this case will be 4n/2 squared, right? And this is something important to realize, is that because our n has changed through this recursive call, essentially, right? Our n got divided by 2. Our work also gets impacted by that, right? By the same amount of our input. Right? And let's say this right type level is ith level of 0, and then ith level of 1 in this case, right here. And let's draw one more, basically another ith level of 2, just for first another sanity check. And assume that there's another 8 branches coming out here. And right here, there should be another input and then work at this level. And input in this case will be, well, in this case, it will be n divided by 2, right? Because we had 2 recursive calls consecutively into here. And there'll be n/4 in this case. And like I said before, because our input n got divided by 4 in this case, our work also gets dependent on this input too. And so it'll be n/4 squared. And it goes down to some base case, right? Where each base case basically is when our input is basically, I guess, like n less than equal, when our input is 1 and our work at that base case is 1. And we don't know what our ith level is, and we'll have to figure this out later. right? So we have this sort of tree structure, and we're trying to kind of like combine all of these work done in order to find out total, like the asymptotic analysis. Right? And so to, I guess, go back to our first question, what is the size of the input at level I? Well, size of the input is asking what is our input at here, right? So we start with n, and the next call is n over 2, and next call is n over 4, and next call is n over 8, and so forth on. And we can assume that we can kind of like relate this to our ith level essentially, right? At ith level, our input basically gets, or can be modeled by n over 2 to the I, right? And just for sanity check, we can see that n over 2 to the I equals to 0 is n, right? And n over 2 to the I equals to 1 is n over 2, and so forth. And so this makes sense, right? And B asks, what is the work done by a single node at non-base case level of I? And it's asking, given a single node, right? That is not the base case, right? We're not talking about this base case right here. At this given, at a single node, like, can we model this single node's work done, right? And well, it's sort of like how I drive, the size of the input at level I. Well, we know that it has to be 4 times something, right? But in this case, well, we know that at each level, because our work is dependent on this input, and our input is essentially kind of getting smaller by this ith level, right? This is the same thing as saying n over 2 to the I squared, right? And just for sanity check, we can also like kind of plug in our I value here. We know that when I is equal to 0, this whole entire input is going to be n, so it's 4n squared, like we have derived here. And when I is equal to 1, we know that if we plug in I equal to 1 here, it's 4 times n over 2 squared, and it's right here. And so forth on, right? And so we can see that right here, this n right here, in our work done at a non-base case is directly related to this input size. Essentially, this thing right here is directly related to this input size. All right, and C asks, what is the number of nodes at level of I? It's asking how many nodes do we have at each level essentially, right? We know that at I equals to 0, there's 1 node, and I equals to 1, there are 8 nodes at that level, and so forth on. And this isn't asking you how many total nodes there are, it's asking you how many nodes are at level of I, right? So we know that at I equals to 0, there's 1 node, I equals to 1, there's 8 nodes, and I equals to 2, it'll be 16 nodes, and so forth on, right? No, it won't be 16 nodes, it'll be 64 nodes, sorry. Math is hard. All right. So we know that that means that it seems like this is being, our number of nodes are being increased by power of 8. So basically this is 8 of I, right? And we can kind of see that through our recursive calls of 8 right here. And D, what is the total work done at ith recursive level? And this is basically asking, what is the total amount of work done at the whole entire recursive level? So it's not asking you how much work did I do across the whole entire base case level, but like before our base case, we know that we all have like this whole entire like recursive calls, recursive trees, and then we just got to add up all the work done by this whole entire recursive work, right? And that's what it's asking. And in order to do this, you can think of this D step as sort of like I guess how I could think about it, total work at recursive level is sort of like total number of nodes at recursive case times total number of total work at recursive case, right? And this sort of makes sense, right? In a sense, like if you want to find out the total work done at ith recursive level, what we're doing is essentially we have to basically add up how much did I work on, did I do in this one node, how much did I do plus how much did I do, how much work did I do in this node, how much work did I do in this node, and so forth on. So I'm adding up all the work done at this basically recursive case. And well, and that's sort of like all this, you know, the summation of all those nodes. Or we know that that could also be, you know, like converted into total number of nodes at recursive case times the total, the work done at the recursive case, right? And this can be kind of modeled through. Well, we know that total amount of, how many nodes do we have? Well, we know that there are a to the I number of nodes at ith level, and then we know that at in a recursive case, we know that each node does sort of like 4 to the n over 2 to the I squared amount of work. And we can kind of simplify this into a to the I times 4 to the n squared over 2 to the I, and which is also equivalent to a to the I times 4 to the n squared over 4 to the I. And we can simplify this further. We know that this will cancel out into 2 to the I, and I guess we can simplify to 2 to the I times 4 to the n squared. All right. Now, E asks, what is the last level of the tree? Well, last level of tree is, it's asking you what is our I, essentially. Like we don't know our I is, and we kind of figure that out, essentially. And how do we figure that out? Well, we know that our input is modeled by this function, n to the 2 to the I. And eventually our function will have to get to our base case, right? Right. And we know that we reach the base case when our input size is 1. Right. And using that, we can kind of figure out our I in that case. So what I mean by that is, for E, we know that our input is given by n to the 2 to the I. And eventually our input is going to reach to 1 when we reach our base case, right? And basically we're kind of like figuring out this I value, right? And so if we were to figure out what this I is, well, it's sort of like another math problem, right? That'll be n over 2 to the I, and we can get that this becomes log 2 of n equal to I, essentially. So that means that at log 2 of n is when we reach our base case, and in terms of ith level. So this would become log 2 of n. Okay. And F, what is the work done in base case? I believe this is asking you how much total work is done across the base case. And this is the same idea. A total work done in base case is given by total number of nodes at base case multiplied by work done at base case. And this is sort of like the same idea with how we solved the total number of work in recursive case. Instead, if you think about it, we have each node doing some, a base case amount of work. and then we're just kind of multiplying the total number of nodes at that base case, and that'll give us like the total number of total work done at base case, right? At base case. And so we know that each node can do one amount of work, right? Given by this, recurrence, right? At each node, it does one work. And how many nodes do we have at base case? Well, we know that the number of nodes are given by a to the I, right, from C. And we know this I, right? We know that we reach base case when I is equal to log 2 of it. Right? So we can substitute this in this I, and that this function can be modeled by 1 times log 2 to the n, essentially. And this is like the total work done across the whole entire base case. Right? And combine, G asks, combine your answers from previous parts to get an expression for total work. So G is basically saying, well, we know we know that this total work is kind of given by recursive work plus base case work, right? And we kind of have to solve these, recursive work and base case separately, because we know that recursive work, it does different amount of work compared to base case work, and we can see that in a recurrence, right? In our base case, we do constant amount of work, but in the recursive case, we do like 4n squared amount of work. So because of that, we had to kind of calculate it into 2 different parts, and we did solve that essentially. So we know that in part D, we solved what is the total work at the ith level. So given a level, how much work did the recursive work do? And we know that we have to kind of go from that we have to add up all the recursive work from I equals to 0 to I equals to 1, all the way down to our base case, log 2 n, but not to the base case, like not including the base case, but like a level above base case. And what I mean by that is we know that we have to add up all the recursive work in our tree, and that's sort of like a summation, right? And what I mean by that is, like, we know that we start with I equals to 0, and we know that we reach our base case at log 2 of n. But we know that we don't want to add up to our base case, right? Because we know that our base case work is given by our base case work that we have founded on the part F. Part F. And so we want to go 1 level above that. And we know that the recursive work at ith level is given by our part C, which is basically 2 to the I times 4 to the n squared, I believe is what we got. You're right. And plus our base case work. Well, we don't have to do any summation in that case, right? Because there's only 1 level to that, and we kind of figure out how much work was done across the whole entire base case. So there is no summation for this part. So we can just kind of plug this in for our base case, our part F, essentially. And we can get 8 to the log to the n for that. And this basically tells us how much work, total work was done across our whole entire tree, essentially. And we did that so through finding the recursive work and all the base case work. And so I guess G, H, and I is basically sort of like solving this this summation so that you get some kind of closed form. And just for a reminder, closed form, informally, you can think of it as kind of like using all the summation rules that we have learned in class, and to kind of find out like to get rid of this whole summation, and we'll get some kind of function. And I won't do that in this video because this isn't a math class, but the solutions to this does kind of go over the math portion of it if you're interested. And so I do highly recommend looking at that one if you're interested in solving the closed form. That being said, I think one thing I want to really point out is that unlike the section problem that we have went over in class, the input and the work is different. It's not always guaranteed that your input and your work is going to be the same, right? And because of that, just do watch out and do make sure you kind of draw out a diagram to make sure that your input and the work is not the same all the time, like how we did it in our section problem. Yeah, I think that is all for this problem or video. That being said, if you have any other questions, you can feel free to post on Piazza on how I approach this, or if there's anything unclear about my step. Yeah. All right, good luck, everyone.